charts. I think those are so funny. Just the whole premise, you know. So remove themselves from the gene pool. I am so pleased that everybody's here today because this is a critical day. I mean, this is the worked out problem on the next exam is the cycle problem. And so I'm really glad that we're all here so that we can start at the beginning and get this down. Because really one of the main activities in thermodynamics is, especially for heat engines, is to figure out what the cycle is and to actually do the math related to the cycles. So we'll do a simple cycle problem first, and then we'll turn up the heat, as it will, and get into isothermal expansions and compressions, and so we'll also learn a lot of vocabulary words today. So this is the review of the equations that we need to do these cycle problems. We need to know things like enthalpy changes, internal energy, but also these bottom two, this at constant volume and at constant pressure, these different changes in enthalpy and internal energy. So these equations are especially useful. And then this relationship. So those right there we're carrying forward from the previous lectures. And you will use them over and over again. So even if you don't know what happened between point A and B, if you know that there was a temperature change, you could calculate the change in internal energy or the change in enthalpy, right? So that's helpful. You're like, well, at least I know this is between two temperatures, so I could calculate the internal energy change or the internal enthalpy or the enthalpy change. Did you at least get those written down? Okay, if you have the notes. All right, let's go on. And so before we want to begin any of these problems, you first begin with the axes. You look at this, and this is a PV plot. So we have pressure versus volume. And so if you have a straight line on any of these plots, you need to know what axis you're dealing with. So up at the top, we see a straight line. And so that's, it's the same pressure all the way across. And so we would know that that's an isobar. And then we have another straight line in this cycle problem. It's a vertical line. So we look at the x-axis and we see that that's volume. And so we know that that's the same volume. And so do you know the name for that one? Isochore, C-H-O-R, isochore. I think it has an E. So that's an isochore. So that's the same volume. So we have the same pressure across the top, same volume down the side. And then we have to be told, if you have a curved line in any of your cycle problems, you either have to assume or be told what that is, because it could be either an adiabat or an isotherm. And so you'll get different answers depending upon which is which. So the adiabat is steeper than the isotherm, but you can't just look at it and know. So you've got to be told that. Either it's an isothermal expansion or compression or an adiabatic expansion or compression. In this case, we're told that it's an isotherm. So we know that the temperature at point 1 up here is the same temperature as point 3. So those are on the same temperature line. And if you think back to PV equals nRT, pressure is inversely proportional to volume. So P equals nRT over V. If you pick a particular temperature, that's the relationship right there. You pick a different temperature, you'll have a different isotherm. But everywhere on that line is the same temperature. And those smooth lines are reversible. So that's a reversible isothermal expansion or compression. Now, how do I know which is which? Compression or expansion? You've got to know the direction, because you got to know V initial, V final, right? And so this right here is the arrow. You can see the arrow there. And so that means it's compression. Up here, this arrow is going to the right, so that's expansion. And the isocore is the same volume, so it's not compression or expansion. It's the same volume, so nothing's happening there. We are changing temperature and pressure, but we're not changing volume. Any questions about this? So this is how the problem might be stated. You've got this cycle, and it says 10 moles of helium is taken through this particular cycle. Calculate the heat, the work, the change in internal energy, the change in enthalpy for each of the segments. So you calculate all of those properties for all four or all three segments. A segment is a transition from point 1 to point 2, or point 2 to point 3, or 3 back to 1. So each of those are called segments. So you calculate them independently. What's happening on this segment? Q, W, delta U, delta H. What's happening on that segment? So you move your way through, and then at the end you add them all together. So you can see what the amount of total net work done and how much heat you put in. If you take that ratio of the work, you put in a certain amount of heat and you got a certain amount of work out, then that's going to be your efficiency. Of those 100 joules of heat going in, how many joules of work did you get out? And we want that to be as high as possible. So before beginning any of these calculations, you want to see if any of these processes apply. So like isothermal processes, because delta T is 0, then you know the internal energy is 0 and the enthalpy is 0. So these are the things that are not really equations that you write down. These are just things you know. If it's isothermal, heat and enthalpy and internal energy don't change because it's isothermal. And this is stuff you just have to know. I can't help you with this. You've got a sheet of equations on your note card. Which one applies, right? Well, if you were to apply the delta T, you know, that equation that contains delta T for this segment, you would see that delta T is 0. And so you might waste some time writing all that out, or you could say, by definition, temperature hasn't changed, so I know that delta U and delta H are 0. Okay, here's another one. If you see an adiabatic, now we don't have one in this cycle, but if we did, if we had that curved segment and it said adiabat or adiabatic, then we would know that heat by definition is 0. So there's no change in heat. An adiabatic system is isolated or insulated. So the heat can't flow from the system to the surroundings. It either happens too fast or there's an insulated wall. And so there will be some change in internal energy, and the change in internal energy is the sum of heat and work, but if heat is 0, then the work is non-zero. So the internal energy change would just be equal to the work. And then constant volume processes. If it's a constant volume, then you can't be doing any expansion work. So work would be 0 in that case. Therefore, delta U would be the heat. You know, if you're not paying attention or you don't remember these things and you did try to calculate the work, what are you going to end up with? If you think it's a reversible isothermal expansion, you'll have V final over V initial, and that'll be 1. And what are you going to do? Take the natural log of 1, which would be 0. So even mathematically, if you put V final and V initial in and they're the same, you're going to get 0 work. Or if you have minus P external times delta V, and delta V is 0, you're going to have 0 work. So the equations will lead you, but you can save some time by just knowing these things. And so let's go through and put these assumptions on here. We're looking at the top segment, and we see that that's expansion against a constant pressure. And so we have a work equation for that. Work is minus P external times delta V. And so we have the volume at spot 2 and the volume at spot 1. And so we take that delta V, and we know that P external would be the pressure of those 2 points. We also have over here constant volume cooling. Okay, How do we know it's cooling? Well, you know we're going down in pressure and we're at a constant volume. And the only thing that can change is going to be the temperature. So how are you going to get the pressure to drop? You're going to cool it down. Okay, so constant volume cooling. And that's, again, looking at the cycle problems, you have to use your common sense, what you know about gases. If I cool things down, the pressure will drop if I'm in a container, a rigid container, constant volume. Number of moles is the same for this problem, 10 moles of helium going around, so we know we're not changing the number of moles. So the only three things that can change are temperature, pressure, and volume. And then that isotherm going up, we know because it's delta T equals 0 that U and H are 0 and that Q equals minus W. So if we can calculate the work, we just change the sign on that number and it's the heat. Notice how to do all of these equations, we need things like the pressure, we need the volume, we need the temperatures, okay? And so that's really, I say the first step is looking at the situation, seeing if there's any isotherms and so on. The second step is pulling the equations and thinking about those. But the third step, before you do any calculations and try to use these, is to come up with what I call the state variables table. What are your state variables? N, P, V, and T. So you need all four of those variables for every point in the cycle problem. So you just make up a table that has all four variables and all of the points, all of these destinations. That way you can do the deltas between point 1 and 2, or 1, 2, and 3. So that's what this is, the state variable table. And so I have all of the points across the top, point 1, point 2, point 3, and then the state variables going down the rows. Now I go ahead and put N in there just because it is a state variable and you can see that it doesn't change. But it's nice if you're going to use the ideal gas law to have N so that you know what to put in there. Don't, if you're told that it's 10 moles and you don't write it in your state variables table, you might forget and use 1 mole and then you'd be off by a factor of 10. So that would mess you up. So go ahead and be meticulous, and for your state variables table, use all 4 state variables, okay, so that you can have everything you need to know for each piece. And so we have these points up here given, this 10 atmospheres in 1 liter, 10 atmospheres and 20 liters, and that's everything that's given in the problem. So we have this point here. So these variables were given for that point, and these here were given for this point. And so at this point we can write down quite a few state variables, but we don't have everything. And so this is like a game of Sudoku, only better. Okay. You've got an incomplete table, and you've just got to figure it out. So this is part of the cycle problems, is figuring out your state variables. And our friend is the ideal gas law. So we're looking at this at point 1. We're told that it's 10 moles. We're given we're given the amount, we're given the pressure and the volume. So we have 3 out of the 4 variables. So we can calculate that temperature. And then the same thing for point number 2. It's the same pressure, and we've gone up to 20 liters. And so we have the pressure, we have the volume, we have the number of moles, and so we can calculate those. Of course, we also know, let me go back, we also know that 1 and 3 are on the same isotherm. And so you can do this in any order, but if I looked at this and I said, great, I calculated the temperature for spot number 1, I know by definition that's the same temperature as spot number 3, because it's on an isotherm. So sometimes you're looking at this and you say, well, number 3, over here, I don't have enough variables. I've got the volume, I've got the number of moles, but I don't know the pressure, and I don't know the temperature. But now that I've calculated the temperature for spot number 1, they're on an isotherm. That's a mental skill that you have to have. When you see things on isotherms, they're the same temperature. And so when you're filling out your state variables, sometimes that's the key to the puzzle. So you're looking at this column over here, like I've got 2 variables and I need 3 to solve the problem. So your third one comes from that isotherm. And so now for spot number 2 or spot number 3, we have 3 of the 4 variables. We have one equation, one unknown, so it's pretty easy to solve. So we can put in pressure 2, volume 2, divide by nr, and we end up with 243.7 Kelvin. That's the temperature at point number 2. And then we've got the temperature 3 and volume 3. We can solve for the pressure at point 3. So that pressure dropped quite a ways because we went from 240 Kelvin down to 12. So it really dropped. This really isn't a realistic cycle. I don't think we could operate a cycle like this at 12 Kelvin, but it is helium, so it's not going to condense just yet. I want to stop here for a little bit just to give you time to ask questions or clarify things, because this is a key step, not just in cycle problems, but any problem. Taking a thermodynamic problem and breaking it into the pieces. I know somebody has something they want to ask.
Okay, so with the tables, I know this one's for an isotherm. Would it be the same if it was an adiabatic?
The difficulty if this was an adiabat is you couldn't have that temperature connection.
Okay.
But if you had, trying to think if there's any other way to get through this if you didn't have that isotherm, okay, for this particular problem. You may not be able to solve it unless you know. Now there are some adiabatic relationships that we'll learn later that if you know the pressure and volume of those 2 points, then you can get the temperature at the new spot on an adiabat. So we have some adiabatic relationships, but the isotherm is easy because it's isotherm, same temperature. But the adiabatic relationships, we do have some equations that can get us those other points using an adiabat. And so we'll cover that actually next lecture. We'll get into those adiabatic relationships. So if I have the pressure and volume for point 1 and the pressure for point 2 on an adiabat, I can solve for the volume on that point 2 using these relationships. They're kind of strange because all 3 state variables are changing at the same time. Pressure, temperature, and volume on an adiabat. Here, only pressure and volume are changing because the temperature is the same. Good question though. Yeah, so if it's an adiabat, there's some like 3 little relationships. You can relate pressure to volume, pressure to temperature, and temperature to volume. So the 3 different pairwise relationships you can do for an adiabat relationship. That's going to be definitely no card worthy, just to have all of those on there. Okay, so let's do segment 1 to 2. So we're going from point 1 to point 2. That's that first segment. We call them segments or legs. Sometimes we'll say the first leg of the cycle, the second leg of the cycle. So legs or segments. So work is P external minus delta V, or no, times delta V. And so we have negative 10 atmospheres, V final is 20 liters, V initial is 1 liter. Don't make the mistake of saying, oh, that's delta V equals 20 liters. No, it's subtract that 1. It's 19 liters. Okay. And then we have it in liters atmospheres, which we know is not joules. We'd like to have joules. And so we multiply by that conversion factor, 101.325 joules per liter atmosphere. And we end up with negative 19.3 kilojoules. So it did work by pushing back this constant pressure force, whatever that force is. It could be a piston or it could be the atmosphere. But if we want to actually get the work out of this thing, it would be a piston. So it's pushing back against this piston, and it's doing an expansion, and so that's we're getting work out of the system. That's negative 19 kilojoules. So then we want to calculate delta H. You could do this many different ways. We could do U first. We could do Q. But let's go ahead and get delta H. So that's the heat capacity at constant pressure times the number of moles times delta T. So T final minus T initial. Now you're looking at that 5 halves R. That's Cp. And you may say, wait a second, this is a monatomic gas. 512 looks, 5 halves looks like a diatomic, right? But this is CP. So a diatomic helium, no, a monatomic helium just has translational motion. So it's 3 halves R for CV. And then you add another 2 halves because you're doing CP. So that relationship, let me write it on the board just to remind you. Right, that's just 1 R. And so that's where we're going to get the 5 halves R for CP. Okay? And that's 3 halves because helium only translates. It doesn't rotate, it doesn't vibrate, so it doesn't have any other degrees of freedom. It just has 3 translational degrees of freedom, which gives us the 3 halves R. So we're connecting that first piece of the course into these cycle problems. So then we have 244 Kelvin minus 12 Kelvin, and so then we end up with 48.2 kilojoules. So that's the delta H. It's positive, so that means energy's gone into the system in terms of heat. Okay, so then the internal energy change, here we're just using this first piece, the CV, the 3 halves R, times the number of moles, times the delta T. So 244 minus 12, we end up with the internal energy change of 28.9 kilojoules. It's positive, so internal energy is increased. And so when we have that equation, delta U, delta U is Q plus W. We've already calculated W. We've calculated delta U. And so just solving for Q, we just take the difference between the two. So we end up with 28.9 kilojoules minus a negative 19.3 gives us 48.2. And in another way, I mean, you could have said that Q is equal to delta H, and we would have gotten the same answer. You see delta H is 48.2 kilojoules. So this is a positive heat value. So we put in 48 kilojoules, and we got 19 kilojoules of work out, just on that leg. So that segment, we put in heat, and we got some work out. Okay. And so then we'll do this. So that's all the variables for that first segment. Any questions on that? How you would, I mean, where would you have gotten stuck, I guess, is a good question. I suspect you would have had a hard time knowing which equation to use, right, with all of these equations. But just think about them. You start with things like this and say, well, I've got this equation, delta U equals Q plus W, but I don't know these two things yet. It's like, well, okay, I need W. Wait, I've got an equation for W, P external, delta V. I'll use that one. And so then you do W first.
Yeah, the homework, it lists them, but it's actually Q and then W, and I was trying to go from Q to W, and I'm like, wait, I need both of those to get U. So
yeah, and so then, and then don't forget the delta U. We know that one because there's a temperature change. And so there's other equations. So in that case, you have these two equations. And so if I'm looking, I want to calculate the internal energy change, and I have these two options. You say, well, for this one, I'd have to calculate W, but I don't know Q yet. But this one, I know delta T, and these two I can figure out easily. That's the number of moles and the CV. So that one I can get a handle on first. And so you might have calculated this one first. So that's why there's really no order to this. I can't say always calculate the internal energy first or the heat first, because you may have certain things that stand out to you. So this is also a puzzle. It's not a table puzzle. It's not like Sudoku, but it is definitely a puzzle, trying to figure it out. So let's do the next segment. So segment 2 to 3. The work is easy because we have delta V equals 0. So the work is 0. So we're not getting any work out of the system with this drop in pressure. We know there's a huge change in temperature. So we have that internal energy, 10 moles times 3/2 R. T final is 12 Kelvin. T initial is 244. So this is negative. So energy is flowed out of the system. Okay. Negative. The system has lost energy, 28.9 kilojoules. If I was in the form of heat, okay. So here's the delta H using CP, negative 48 kilojoules. And then again, rearranging this, we know work is 0, and so we know internal energy, so we can figure out what Q is. And so it's the opposite. It's just negative 28.9 kilojoules. Because work is 0, because we're not changing volume. So this one was pretty easy. When you had no volume change, work is 0, and that helps in other areas. Any questions on this? Same equations, just figuring out with different state variables. So you're always working between 2 columns in that state variables table. And it's eventually you'll reach the point where it's not hard, it's just tedious, right? Calculating all these different things. But that's a good thing, because you can do tedious. You may not like it, but you know, as long as you understand what you're doing, and you're like, golly, I just got to hammer through this, get this equation and do it, then you understand it. Let's do that last one, this isotherm. So, the same temperature, so there's no change in internal energy, no change in enthalpy, because those are both delta T equations. So delta T is 0, you know those two are 0. I still like to see, you show the equation and say, this is 0 because delta T is 0. And so you can just kind of talk to me that way. Show the equation you would have used, draw an arrow, like do this. You say, this is 0, therefore delta U equals 0. That would be great. You don't really have to do any math, but just show me that you knew how to calculate it, and that because delta T is 0, then this value is 0. And so then we have 0 here for delta U is equal to Q plus W. And so these are going to be equal but opposite sign. So when we find one, then we can just change the sign and get the other. So we know this is an isothermal compression. We have an equation for the work in that case, a reversible isothermal process. And so that's minus nRT, natural log of V final over V initial. So V final is V1 from our state variables table, and V initial is V3 in our state variables table. So we just put all of those numbers in there. The V1 is 1 liter, the V initial is 20 liters. We're at 12 Kelvin, 10 moles of gas, and the gas constant. And so we end up with 3 kilojoules of work. And it's a positive number. Does that make sense? Always check your signs to see if it makes sense. In this previous leg, we dropped the pressure and dropped the temperature, and our delta H and delta U were negative. That's telling us the system lost energy. Well, yeah, how are you going to get the temperature to drop? You're going to suck energy out of the system, and the temperature's going to drop. Here, we're compressing our system. We're compressing 10 moles of helium, and the work term is positive, right? We're doing work on our system. We're resetting it by pressing it into a smaller space. So it should have a positive work value when we're doing compression. And let me speak a little bit about this, because this is how heat engines work. We want to heat up the gas and get energy into our gas, and that gas is going to push on a piston and help us out. It's going to do work for us. And then we don't want to push back against the hot gas, because that's hard. But we've got to reset the system. Think about the piston. The piston goes in both directions. So we use the gas at high temperature to push the piston back, and we get some of that work. And then we want to cool everything down and compress the gas at a lower temperature. It's easier. Think about it. If I'm compressing a gas at a lower temperature, it's easier to compress. And then I raise the temperature and I get the gas to push back. And so we deal with two temperatures and we reset the system. We reset the system at a lower temperature, raise the temperature, and get it to push for us. So there's always a leg where it's the power stroke, where the gas is pushing on the piston and we're getting some work out of it. But we got to pay our taxes, right? We got to pay back in, and we've got to use some energy to reset the system. We got to get the piston back to its small volume space. And so that we're actually putting work into the system, and we want that to be as easy as possible. We don't want to use a lot of joules resetting the system. But this leg going from 3 back to 1 resets the cycle. And it only took 3 kilojoules to do it. So that's great. It's because it's at 12 Kelvin. So if we could really implement this system, it'd be a great engine. You know, we could get it down to 12 Kelvin and reset that with only 3 joules, and then we could push with 19 joules. And that'd be great. Now it's an isotherm, so if we put in 3 Kelvin of work to keep it the same temperature, we're going to have to suck out 3 Kelvin of heat. And so the heat is the equal magnitude, opposite sign. And so we would do this in like a temperature bath where we compress the gas, we put 3 kilojoules in, and that heat flows out into the temperature bath and keeps it at the same temperature. Okay, yeah.
Oh, the 3 dots that are upside down.
Oh, because. Yeah, if you take the therefore and flip it upside down, it means because. Thanks for asking, yeah. So that top one is they're both equal to 0 because delta T equals 0 instead of a therefore. And I'm glad PowerPoint cooperated. In the past, sometimes the fonts from, it's the same computer, but sometimes in lecture it would show up as a mailbox. Some wingding or whatever. And so up here it would be, you know, delta H equals 0, mailbox, delta T. I was just so frustrated. Yeah. So, okay. So this is segment 3 back to 1, and we've reset the system. So we have all 3 segments calculated. And now let's put them all together. Let's look at the total, you know, circuit. And so for the cycle, for the whole cycle, delta U, that's delta U for 1 to 2, 2 to 3, and 3 to 1. We had 28.89 joules, kilojoules, 28.9, negative 28.9 kilojoules, and then 0 for that third leg. So we get 0 change in internal energy for the cycle, 0 kilojoules. And delta H, 0 kilojoules. Now, that may make you scratch your head, right? But remember that delta H and delta U are what we call state functions. It doesn't matter how they got to point 1. If you're at point 1, you're going to have a certain internal energy and a certain enthalpy. And if you go around the world and come back to point 1, you're going to have the same internal energy and enthalpy. Because it just depends upon N, P, V, and T, what the internal energy and enthalpy are. And so it doesn't matter what you do, if you get back to state 1 successfully, the whole sum of all the U's and H's is going to cancel out, and you're going to get 0. Yeah, so that's actually great. That kind of is a check on your math. If you get through a cycle problem and the delta U for the whole cycle isn't 0, there's a problem. So this is a nice anchor point. You can use those two to check your math. Look for problems. So I'm going to put here, useful. Check. And then the work and heat do depend upon the path. In fact, we construct different cycles so that we can get more work out and use less heat to do it. And so in this case, the work for the cycle 1 leg 1 and 2 was negative 19.3. That's when we got work out. The isocore gave us no work, required no work. But then the recompression, the resetting of the system, 2 to 3, took 3 kilojoules of work. So it reduced our net out to 16.3 kilojoules. So that's how much total work we got out of the system. The net amount of work that our system did for us was negative 16.3 kilojoules. And then the heat was 48.2 in. So to increase the volume at that constant pressure, we had to really increase the temperature from 12 Kelvin to 244 Kelvin. We put a lot of heat in on that first leg, 48 kilojoules. We pulled some heat out to get the temperature back down at the same volume at 28.9 kilojoules. And then we sunk a little bit of heat, resetting the system. We compressed it for 3 kilojoules, and we pulled that heat out as we were doing that compression to keep it on the isotherm. And so then that used up 3. So our net heat was 16.3 kilojoules. But net heat really isn't a thing. It's heat in that's a thing, because I had to pay for that. Right? Whether it's nuclear energy, whether it's wind energy that's using the heat from the sun, that's kind of free. But the equipment's not. Or coal, natural gas, gasoline. I'm burning something or using something or refining something that I'm using to put heat into the system. So all I care about is the heat in, not the net heat. And so that's why efficiency takes only the positive value for Q. So looking in that row, there's only one positive number, and that's plus 48.2. That's what I had to spend my money on. I had to put that 48.2 kilojoules into the system, and I got 16.3 kilojoules out. The net work out is what I get to keep, but I put in 48 kilojoules. So that's how heat engines work. It's the heat in and the net work out. Not just the out work, but the net. Yes?
The next time you run this cycle, do you only have to put in 31.9 to get back?
No, you got to do it all again. So you constantly have to supply 48.2 kilojoules, and you're only going to get 16.3 kilojoules out.
Right, but can't you use the 16 that come out to start the next cycle and only add a little bit more in?
Oh,
Kinda
you're
like
just
a bicycle is easier to pedal once you've already started.
I guess we're not accounting for like any kind of startup. This is once it's running. So every time it cycles, this is the best you're going to get. Yeah. So we don't know how we got to 0.1. Yeah. So we might have had to do some things to get to 0.1. But once this cycle's going, then it's 1, 2, 3, 1, 2, 3. And we're going through this. So that's a good point, actually. To get the thing started, you may have to just put in even more heat. But once it's going, this is the best it's going to do for you. Yeah. Yes.
I noticed that it's an absolute value for the work, but you said it's kind of absolute value for both Q and work.
Well, it's that work for the cycle. So that's the net work. So it's everything all added together. And it's a negative number because it's doing work. So the system's doing work. And so we didn't want to have negative efficiencies. So that's why we're just cutting the negative sign off of it. So it's 16.3 divided by 48.2. Yeah, so that's what we end up with. But 16.3, since it's work for the cycle is negative, we're just saying let's have a positive efficiency, and it's going to be 34%, which is
Why don't you just
pretty
use
good.
Q for the cycle? Because Q for the cycle is work for the cycle. Except
Yeah,
for the
yeah. But I mean, it's just work over heat in. Yeah. Because so this is the efficiency for this particular cycle. Very difficult cycle to do because the range in temperatures, 244 to 12 Kelvin, yeah, that's going to be real tough. So that's a cycle problem, your first cycle problem. This is like a warm day. Mark this on the calendar, you know. Yeah. So
is the overall, towards the end, you're going to want us to work through all that to get the efficiency, the percent?
Mhm.
Okay.
Yeah, so when you get to the efficiency, it's like you're done. You've got the whole cycle, you know what every leg is doing, you got the net amount of work you're going to get out of it, and then you've got the efficiency of that cycle. Now we'll compare that, say, to a Carnot cycle. So a Carnot cycle is like the most efficient possible cycle. All 4 legs are reversible. Reversible processes, because they're smooth, we get the most work out of those, or the most efficient heat and work conversions. And so we'll look at Carnot cycles next time. So let's compare this though to a Carnot cycle. There's a very easy equation for the Carnot efficiency, and that's just the ratio of the cold to the hot temperatures. So if the cold was 0, it'd be a perfectly efficient engine. You see that temperature, cold TC over TH, 1 minus that ratio is your efficiency for a Carnot cycle. So that's the best you could ever do. And in this case, it's 12 Kelvin over 245. So if this were a Carnot cycle with those 2 temperatures, it'd be 95% efficient. Yeah, that'd be amazing. Okay. Our gas and diesel engines, gasoline engines are around 25% efficient, and diesel are about 35%. And so they're not Carnot cycles. They're, they're, plus the hot, the cold temperature is really the thing that limits you. And the exhaust coming out of the tailpipe is still pretty hot. If we could get that to drop temperature before it leaves the cylinder, then we would get a more efficient engine. Or if we could raise the high temperature inside the cylinder to get more push, then it would be more efficient. So you can raise the high temperature, or you can shrink the cold temperature, and you make the engine more efficient. But eventually you run into material problems. How do you get that combustion to be hotter in there before it starts to melt the head or whatever? You're going to use aluminum pieces because they're lightweight and easy to move, but you've got a high temperature combustion going on, so you put steel sleeves in there. It's a real problem. So it's no conspiracy, it's just tough. And so then we can look at what kind of heat, what kind of work we would get out of this cycle. If it were a Carnot cycle with those 2 temperatures, we'd get 45.8 kilojoules instead of 16. So our improvement would be 2.8 times if we were able to get a Carnot cycle to run at these 2 temperatures. So that'd be fantastic. Let's look now at the Stirling engine. I'm going to try to get it working for us next time, and then we'll go through this next part of the notes. But I've got a heat engine here. So come on up here, show and tell. We've got 2 minutes. Let's go. And it is finicky. Sometimes it works. There's just a lot of friction on the pistons. And so I've got 2 pistons here, the crank, a little electrical generator, and an LED light. So the hot side, cold side, got to heat it up and then you can get started. You see the light? It's going to be. So this is that initiation which we're talking about. Putting in a lot of work. Yeah.
What is the change in the light indicator?
It's just giving, it's current, so it's spinning the generator and giving us, the green and blue and red is just for fanciness.
Oh, okay. That would have been
And if you had an ice cube and you put it on the cold side, it'll speed up.
Oh,
Yeah.
wow.
So we're just using the expansion of the gas and the cooling of the gas. So we heat it up, the gas comes over here, cools down, and sucks that piston in, which resets the other one, which heats up. So it's pumping heat from the flame to this side, and it's giving us work out. That's so cool.
So like, did you just buy this, or did you?
Yeah, that's like $30 on Amazon.
I can imagine
Hear this.
the molecules in there just going crazy.
Yeah, yeah. So that's a heat engine. It's not a very efficient one. We'll look at the legs on this engine next time. Yeah. And the squeaking, it's the pistons are rubber, they're dry in there. I tried to lubricate them with WD-40 and it stopped. So then I had to take it apart and clean it up this morning. That's why I was a little late for class. But that's the Stirling engine. And there's a lot of these online. You can find them. There's different kinds. There's coffee cup Stirling engines that you set on a hot cup of water and it'll start pumping and you start turning the wheel. And it's really cool. Yeah, the glass is still hot, so it's still burning. So I want to take this guy and bury it in the ground, and I want to hook a Fresnel lens to focus the sun on that glass, paint it black, and turn solar directly into mechanical and electrical. And all it's got to do is heat up. The sun heats up things a lot more efficiently than it does separate electrons from nuclei. And so instead of photovoltaic, I just want to use the heat from the sun. And I just want to maybe encase that in a block of concrete. So I want to buy like 100 of these and set them up, and then have a row of things that I can heat up with the sun. And then the cold side will be in the concrete in the earth. It's not going to change temperature. And so the hotter the day, the more electricity you get. That's what Thomas might be able to bring up. What's that?
It's like a post-apocalypse.
Yeah, that's right.
The whole off the grid.
Yeah, that's right. Professor the Prepper. Oh, all right, let's get out here so the palms don't fuss out.
Do they use things like that in space, maybe?
Yeah, I don't know if there's any like commercial uses of the Stirling engine, but there might be, you know. Thomas and I are out to change that.
Change the world.
Yeah.
One Stirling engine at a time.
Yeah.
It's
So,
only $3,000 if they're 30 of these.
I just think it'd be really cool to make one of those. Like,
I know.
how like it does.